Hi there, this is Mr. Bainey. Today's lesson is 6.5, comparing properties of linear functions. Our essential question is, how can you compare linear functions that are represented in different ways? So this is the last lesson of the module, and throughout the module, you learn how to write equations from tables, from points, given a slope and a point, from graphs, things like that, into three different forms, right? We have slope-intercept form, point-slope form, and also standard form. Be familiar with all three of those. And then also 6.4, we looked more into transforming linear functions, like what happens when we change the slope and the y-intercept, being able to describe those changes, those transformations. So here we're just going to be looking at a couple of linear functions at a time and being able to compare and even describe how different and how similar they are. So we're going to go ahead and do the Explore, and we're going to look at, we have Dan's Plumbing and Kim's Plumbing have different ways of charging their customers. The function d of t equals 35t represents the total amount of dollars that Dan's Plumbing charges for t hours of work. Kim's Plumbing charges $35 per hour plus a $40 flat rate fee. So we're going to define a function k of t that represents the total amount. Kim's Plumbing charges for t hours of work, and then we're going to complete the tables. That's for both of the plumbing services. So for Kim, K of T is going to be $35 per hour, because T is hours, plus a $40 flat rate fee. And that's compared to Dan's. I'm going to go and write Dan's here just for reference. They've already given it to us right up above, and it's just this. All right, so for 0 hours, Dan's is going to be $0, which is 0, 0. All right, for 1 hour, it's going to be $35. For 2 hours, it's going to be $70. And for 3 hours is $105. Okay, so I can go ahead and, I'm not going to write up all these points, but this is what it might look like. For Kim's Plumbing, we have $35 per hour plus $40. So for 0 hours, it's going to be 40. For 1 hour, it's going to be 75. So I'm just going to be adding 35 for every extra hour that's being added, right? So for 2 hours, what do I have? 110, and then 145. So what's the domain and range values for the function that are reasonable? So our domain is actually going to be the same, isn't it? The hours? The domain is our t, which means, whoops, not at 1. It's having to start at 0, so we can use that. 0, 1, 2, 3. And then is it reasonable to keep going? I think so. So we can go and put a dot, dot, dot. There is certainly a limited amount of time because they can't really spend, hundreds, thousands, millions of hours there. That's not realistic and not reasonable. But they could spend several hours, so I'm just going to put the dot, dot, dot just to represent that. And so the range is going to be different. So let's just say range for Dan. I'm going to put range for D of T. And that is 0, 35, 70, 105, dot, dot, dot. So these are just our outputs, right? And then the range for K of T is 0, 40. Oops, not 0. 0 is not in there. My mistake. We have 40. That's the lowest one. And then 75, and then 110. And then I'm just going to put dot, dot, dot after that. And so what if we were to graph these? If you just start thinking about what these might look like on a graph and being able to compare them. So for, let's just put, this is for Dan here, and for Kim, 0, 0, 135 would be about here, right? 270. So Dan's might look something like this. Kim is going to be at 0, 40, 175, 2, 110. And so hers will look like this. So let's compare the graphs. How are they alike and how are they different? Well, they are alike in that they have the same slope. And we know that from the equation because of $35 per hour, right? They charge the exact same per hour, the exact same. And then for how they're different, well, they have a different y-intercept. Okay, Kim is the only one that charges the $40 flat rate fee, and then Dan doesn't charge anything at the beginning, right? That's why he starts at 0. Okay, so that is relating the description to the equation, and then finally to the graph and how they look, how they're different and how they're the same. Okay, so now we're going to be looking at a couple more examples. We're going to be looking at tables, and then and looking at this thing called initial value and comparing ranges. So let's look at the your turn. So number 3, we're going to find the rate of change for the linear function f of x. So this is actually, we're not looking at comparing functions here for number 3. We're just finding rate of change. And rate of change is the same as slope. Okay. So that means how much is the output changing here? It's changing by 7. And how much is the input changing? It's only changing by 1. Okay, and is it always changing by 7? It looks like it is. Always by 7. And this is always changing by 1. So if you notice it's always the same changes that are happening, you don't need to keep rewriting it over and over again. Our slope or rate of change is going to be, it's really the change in the f of x, the change in the output divided by the change in the input. So it's just going to be 7 over 1, which is 7. Number 4, the rule for f of x in example 1b is f of x equals 6x. If the domains were extended to all real numbers, how would the slopes and y-intercepts of f of x and g of x equals 5x plus 11 compare? Okay, so f of x, you know what, I'm not going to rewrite it again. Let's just box these so we know exactly what we're looking at here. So f of x is there, g of x is here. How do their slopes compare? Well, f of x is steeper because 6 is bigger than 5. And also, g of x has the higher or bigger y-intercept because g of x has a y-intercept of 11, f of x has a y-intercept of 0. And let's go to the last your turn here. We're going to look at an experiment that compares the heights of 2 plants over time. The plant was 5 centimeters tall at the beginning of the experiment, grew 0.3 centimeters each day. The function f of t represents the height of the plant in centimeters after t days. The graph shows the height of the second plant, g of t, in centimeters as a function of time t in days. Okay, so it looks like on the graph, this is g of t, and f of t. F of t is the description that it's 5 centimeters tall at the beginning, and then it grows, let's see, it grows this much per day. Find the rate of change G of t and compare it to the rate of change for f of t. So G of t, rate of change is, well, look at how much it goes up and it goes over. That's rise and run. It went up, it looks like 4, and then the run is 16. So the rate of change, which is the same as slope, is 4 over 16, which is 1/4. That means it grew 1 centimeter for every 4 days, which is 0.25. So for G of t, it's 0.25 centimeters per day. And for f of t, it told us in the description that it's 0.3 centimeters each day. So if we're going to compare the rate of change, which one is faster? And it is f of t. I'm not going to write down the full sentence, but that one is a faster or a bigger rate of change. Okay, the only thing that I want to mention, I must have skipped over it. I recall from your practice homework is that initial value. Initial value means the first output given the lowest input. So you use the lowest input that you have, and then you get your output for that. That's your initial value. That's this right here. So in order to get an initial value, you have to have some sort of domain that's restricted. If I say the domain is all real numbers, we can't really get an initial value because we have an infinite amount of domain values. So we can't do that. Okay, so that's going to be important for your homework assignment when you're trying it out. And that's it for this lesson. Have a great day. Thank you so much for watching.